Hello and welcome to this live stream. So my name is Laszlo and I run Majestic.cloud, this channel. And this is kind of my first live stream here on the channel. I'm going to present you a session that I did at an AWS user group meetup on writing scalable Lambda functions. So what are some of the best practices and anti-patterns that you might want to consider? So let's look at some of the subjects that I'm going to be covering. This talk is split into two parts. So in the first part, I'm going to talk about understanding the Lambda lifecycle. What is the Lambda lifecycle? Understanding concurrency, how Lambda scales, and the different invocation modes. In the second part, I'm going to talk about some best practices on how to write code and also anti-patterns, what you shouldn't do actually. So let's get started. I'm not going to talk about what Lambda is. Probably you already know. I'm going to start with how Lambda works, understanding the Lambda lifecycle. So basically, AWS Lambda is a serverless compute service which receives an event or there is a trigger that invokes the service, and Lambda is kickstarted. It does something. It might also integrate with some other service. So for example, it might integrate with DynamoDB. And then a response is sent back to the client or the source of the event. It depends on the invocation model. And if we look at the anatomy of a Lambda function, you're going to see that there is this trigger that I mentioned. But there's also some other things in play which we're going to discuss. So you have to configure the Lambda function, you have to configure things like the timeout, so how long the Lambda function should run, the memory which is allocated to the Lambda function, and this will decide on how, or this will have as a result that your function may run faster or slower depending on what it has to do. Then your Lambda function has also a runtime, so basically in which language it runs. It can be Node.js, Python, Java, .NET, or some other ones. And it also has some layers which are basically it can have layers, and layers are ways of reusing code. So you can package your dependencies as Lambda layers. And when Lambda runs, it will look at the whole package that you have there. So basically it will do some initialization, but we're going to talk about later. The first thing that will get invoked is the code handler function, and this has a few inputs. So it has an event object and the context object. In the event object, you will have the input from the trigger, or for example, if that is API gateway, you will have in the event object the payload that is coming from API gateway. And the context object has some additional details about the context of the execution. Your Lambda function will also need some permissions. So basically, there are two types of permissions that can be there. So a resource policy. This defines who is allowed to call your Lambda. For example, if you have API gateway as the caller, then you need to have a resource policy which says, okay, API gateway is allowed to invoke my Lambda function. But you can also have, and you will have, an IAM execution role, and this defines who can the Lambda function call, because Lambda might also need to interact, for example, with the DynamoDB database. So in that case, This is defined in the IAM execution role. Okay, now let's look at the life cycle. And one important distinction I want you to make is the distinction between the Lambda service and the Lambda function. So the Lambda service is the service from AWS which runs your Lambda functions. Basically, here you have an infrastructure that is created and maintained and managed by AWS, and this infrastructure runs your Lambda functions. This is the Lambda service. And your Lambda functions are the functions, the code that you upload and which is executed by the Lambda service. And this, the logo that you see right now on the screen, this is the logo of the Lambda service, so not the Lambda function. I will tell you later which is the Lambda function logo. So you have an event which the Lambda service receives, and in response the Lambda service will do a few things. So for start, it will start downloading the code of your function and any layers that you might have with the code. These are dependencies packaged as layers. Then Lambda have to initialize and create an environment for you. And in that environment, it will run extensions. It has to bootstrap the runtime that you have. It will initialize global variables and the temporary space, and so on. And only after that, it can run your Lambda function. And you see, this is here is the logo of the Lambda function itself. So basically, now Lambda invokes your function, and it will always run the handler method when it does so. So what you have here is a longer request because it has to do this initialization of your environment. And this is known as a cold start. So basically, you get a cold start, your request takes a bit longer to run because of this initialization that happens in the Lambda environment. Now, let's say you have a second event that is coming in, and the second event now will only have to invoke the handler method because your environment is warm, it's already warm. So it doesn't have to do the initialization. And if your request runs, it will run faster. This is known as a warm start. Now, this environment in which your Lambda function runs is kept around for a while. This time is not disclosed by AWS, but you can think about 10 minutes or slightly more or less. It depends. And after that, your environment is shut down. In the shutdown phase, Lambda signals the extensions that it's terminating the environment, and it will be removed. So if you will have another Lambda that needs to run, it will have to go again through the initialization phase, and it will encounter a cold start. Now, you might wonder how you can destroy yourself the environment if you want to. So basically, you want to maybe try out something and you want a clean environment. So the easiest way to do that is to modify your code, or just click on the deploy on the console, or just redeploy your function, and that will lead to a brand new environment being created for that Lambda function. Okay, so this is how the Lambda service creates your environment in which your Lambda function runs, and then destroys it. And now you know what is the cold start and the warm start. But let's look a little bit at concurrency. So concurrency, to understand concurrency, let's see the following example. So what you're going to have is, whenever you need to run a Lambda function, you will have an invocation, and that is creating an environment. And you have this environment, and let's say another request is coming in, but your Lambda is still running. In that case, Lambda will create a new environment, a second environment to run your second invocation, the second event that came in. And these are running in parallel, but the third event is coming in. So a third environment is created. So when we see this, we say we have a concurrency of 3. We have 3 environments running in the same time, a Lambda function for us. Okay, but let's say there's a fourth one. And the fourth one will encounter, in this case, an empty environment, because the first environment finished its task, its first function, and our Lambda can now run in the first empty or available environment. In this case, we have a warm start. But another request is coming in. Now we have to start a fourth environment for that. So you see, we have now 4 environments. We have a concurrency of 4. So when you think about concurrency, you have to think about how many parallel invocations my Lambda has at that particular moment. Okay, now your function duration will impact the concurrency, because it's not the same thing to have 4 requests at 1 request per second lasting 2 seconds, or having requests that last more. So let's see this example. We have these 4 requests at 1 request per second, each lasting 2 seconds. So the first request comes in, and it has to run for 2 seconds. But after 1 second, another event comes in, so it's creating a new environment. After 1 more second, our first invocation stopped, and we would have been able to use that environment. And again, after 1 more second, we can reuse the second environment. So the needed concurrency here is 2. So we have to have at least 2 environments available for ourselves to be able to run these 4 requests at 1 request per second, and each lasting 2 seconds. But what if we have 4 requests at 1 request per second, but each now is lasting 4 seconds? So we have a request, after 1 second another request, after 1 more request another 1 more second another request, and after 1 more second another one. So in this case, in order to be able to run these, we need a concurrency of 4. And you're going to see a little bit later why it's important for us to see and understand concurrency. So let's look at a few things then to understand these concurrency factors. Because AWS throws at us a lot of terms, like for example, they say you have a regional concurrency quota. This is a soft limit that is at 1000 initially in your account. And this is shared across all functions, meaning all your functions can have a maximum concurrency of 1000. So you can have 1000 concurrent runs of functions, not just one function, but all functions in your AWS account in a particular region, because these are at a region level. So if you want to understand this, I came up with this let's say analogy in which I use a coffee shop to explain this. So the account concurrency, imagine that you have a coffee shop, and in the coffee shop you have baristas working, and each barista has a workstation where it prepares the coffee. So your coffee shop has a limited number of workstations where the baristas can work, and this represents the account concurrency limit in AWS Lambda. Of course, you can extend your coffee shop and build additional workstations for your baristas. And you can do that also in AWS Lambda, because this is a soft limit. Basically, you have to create a request to the AWS support team, and they will raise this limit for you if you need it. Okay, then you have something called reserved concurrency. This can be set on a particular function, and it's optional. You can say, okay, this function will have a concurrency of 5. You set this reserved concurrency. So basically what it will do, it will reserve a part of this 1000, the initial concurrency quota that you have, to this particular function. And this is important because maybe you have an important function that you always want to have at least 5 concurrent runs. So other functions cannot, let's say, trespass on the reserved concurrency that you have for this function. And in my analogy, the reserved concurrency is like having a specific number of baristas reserved for certain customers who are regulars or have priority, like VIP customers. And these baristas are dedicated to serving those specific customers, and they won't be available for any other customers. Okay, but you also have something called provisioned concurrency. So what is provisioned concurrency? Provisioned concurrency, if you set that on a function, it will create some warm environments and it will keep them warm all the time. So if you have requests coming in, they will not have a cold start if you have provisioned concurrency enabled for a particular function. And this is always a subset of the reserved concurrency, meaning that it cannot be a higher number than the reserved concurrency that you have set on your function. And if you think about the baristas, then provisioned concurrency is like having a fixed number of baristas that are always ready to make coffee, regardless of the number of customers in line. So even if there are only a few customers, you always have, let's say, 5 baristas ready to serve. This ensures that there is a minimal wait time. But that also means that you have to pay for those 5 baristas regardless of how busy your coffee shop is. And this is also true for provisioned concurrency. This is generating extra costs for your Lambda functions. Okay, then we also have something called burst quota. And this is the rate of the initial burst of a function. And this can range from 500 to 3000. This depends on a region, on the AWS region you're operating in. Larger regions have higher burst quota, and smaller regions have a lower burst quota. This until recently could not be increased. It was fixed, but recently AWS announced that this can also be increased now. So you have to create also a support ticket for this. And if we come to the barista analogy, then this is like you having additional baristas who are only called in when there is a sudden surge in customers. Let's say there is a promotion and suddenly there's a huge line of people waiting for their coffee. Okay, now let's dive a little bit deeper in this burst quota to understand it better. So let's imagine you have to scale to 5,000. First thing you have to do, you need to raise your account quota, but because the initial quota is at 1,000. So this is our goal. We want to get to 5,000 requests, but the regional burst concurrency quota is 3,000, meaning that our Lambda function can instantly scale to 3,000 requests. But then it comes the catch, because it will need an additional time to go up to 5,000 requests. And after this initial burst, this is 500 each minute. So each minute 500 more requests are being added. And all the excess requests are being throttled. So meaning that to get to 5,000 requests, you will need 2 minutes, or actually 4 minutes, because each minute you get 500 additional requests. So from 3,000 to 5,000, you have 2,000, that is 4 minutes. This is what you need to count in and know when you need to scale to higher numbers than your regional burst concurrency quota. Now this can be increased. I'm not sure how long it can be, to how much it can be increased, but I suppose it's not an unlimited number. Now, what can you do in this case? If you, let's say, you need to scale to a high number and you just have to do something. You could think, okay, I'm going to enable provisioned concurrency, and provisioned concurrency might solve my issue. But you should know that the same burst quota applies to provisioned concurrency as well. So this will still take 4 minutes to have this concurrency, even if you enable now the provisioned concurrency. But if you know that you're going to have specific spikes in your workload, you can set it beforehand. Excuse me. So if you can predict it, of course. If you cannot, you still have some additional ways. You could use, for example, AWS auto-scaling and provisioned concurrency to do this. The AWS application auto-scaling can be set to schedule and provision concurrency for known peaks. And you can also combine provisioned and on-demand concurrency. Let's say you have known steady load. You know that each day you have about 2,500 requests all the time. So you set provisioned concurrency at that level. And anything that is above that, it will be handled by on-demand concurrency. And in this way, you're going to be able to serve the traffic in a more optimal way. Okay, before we go into other topics, I also want to just briefly talk about Lambda layers. Lambda layers are basically ways to reuse code. These are shared dependencies. Let's say you have some npm packages or things like that that you need to reuse between the functions. You can package those as Lambda layers and attach that to your function, and as a result you will have a decreased deployment package. So when you deploy your Lambda function, the deployment will be faster. Also, you should know that you can have at most 5 layers per Lambda, and these are immutable, meaning that they cannot be changed. They can have versions. So you have version 1 of your layer, but once you created version 1, that cannot be changed. You have to create a new version, version 2, and attach that to your Lambda function. Now, we also need a little bit to know about the invocation types, because Lambda is invoked in different ways depending on the event source. So in case of API gateway, for example, we have a synchronous direct invocation. In this case, when you invoke a function synchronously, Lambda runs it immediately and waits for a response. Lambda returns the function's response along with any additional data like the status codes and function version. In this case, there are no built-in retries for synchronous invocations. Your client will have to retry if it encountered an error. Besides API gateway, the load balancer also invokes Lambda synchronously, and there are some more services like Cognito and so on. Then there is an asynchronous invocation or a push invocation. In this case, basically Lambda sends the event to a queue and it will not respond immediately. There are separate process that is reading the event from the queue and running the function. Lambda will manage this queue and retries based on some settings that you can configure. Services that invoke Lambda asynchronously are SNS and EventBridge, for example. Then you have poll-based or pool invocation, and in this case, it's not the trigger service that is invoking Lambda, but instead Lambda it's going to invoke these services. So, for example, if we talk about SQS or Kinesis, here Lambda will poll the SQS queue and will ask all the time, SQS, do you have a message for me? So Lambda is the invoker or requester. And in this case, the data will be processed in batches. You can configure batches and process more than one event at a time. This is also known as event source mapping. Now let's see how Lambda scales for synchronous and asynchronous event sources. So for API gateway, let's say you have some events coming in to your Lambda function. And what is going to happen if you hit any of the limits, like for example the reserved concurrency or the account concurrency, you will get a 429 too many requests error, and you will have to retry the requests yourself. In case of asynchronous sources like SNS, the situation is a little bit different. Let's say we have an event coming into SNS and that sends it to Lambda. In this case, Lambda is going to place that in the Lambda internal queue and so we'll send it to the Lambda function itself. And then if it's throttled, it will retry it for 6 hours or up to 2 retries if the Lambda fails for some reason, the Lambda function. You can configure this up to 2 retries. Then if these 2 retries fail also, then you can send the event to an on-failure destination or a dead letter queue. Okay, but how about SQS? In this case, Lambda is polling the service. What's going to happen is that you have a message that is coming in, and you might have even 100 messages in the queue or millions of messages, it doesn't matter. Lambda will take 5 messages out of the queue initially, if there are 5 messages, of course. So it will always start with these 5. So you have to ensure that you have at least a concurrency of 5 set on the function to be able to, because otherwise you will get throttled from the beginning. Okay, so that is how it starts. But then, if Lambda detects that you have additional messages, so the number of messages in the queue is increasing, Lambda will add additional invocations, will start new Lambda invocations to process more messages from the queue. Similarly, if Lambda detects that the number of messages in the queue is decreasing, or there are multiple errors processing your messages, Lambda will decrease the concurrency automatically. So it will reduce the number of simultaneous or concurrent Lambda functions. You can also configure something called batch size. So basically with this, Lambda will take more than one message out of the queue, not just one. So it can take 1 or 5 or 10 messages from the queue. And you will have different concurrency needs depending on this, because you have an average message processing time. Let's say you process a batch of 10, but each message takes 4 seconds to process. You will need 40 seconds. That's fine. But you have a batch of messages that each message takes 3 minutes to process. Basically, you're going to need 30 minutes to process all messages in a single Lambda run. But that will hit the Lambda timeout. This is something that I did not mention so far, but Lambda functions can run at most for 15 minutes. So you cannot run for 30 minutes. In this case, what you have to do, you have to decrease the number of messages in the batch. So basically, instead of having a batch of 10, you can go down to a batch of 3 or 4 messages, just to be on the safe side. So this is how Lambda behaves with different event sources. This is how it scales with different event sources. Now we have arrived at the second part of this session, in which we are going to see some best practices on how to write code and how to structure your Lambda functions to be able to scale and take advantage of your available concurrency and things like that. And also at the end, we're going to look at some anti-patterns, what you shouldn't do in this case. Before we do that, let's just see some Lambda limits. So the memory of a Lambda function can go from 128 megabytes to 10 gigabytes. You cannot directly change the CPU allocated to the Lambda function, but as you increase the memory, the allocated CPU will increase as well. You will have a temporary directory storage, a /tmp. Think about this as a small little hard drive attached to your Lambda function on which you can store some files. And this is going to be preserved in the same environment. So if you have the same execution environment, once your environment is terminated, that /tmp space is destroyed. If you have a cold start, you no longer have access to the previous execution environment's /tmp storage. I'm going to show you later how you can take advantage of this. The max timeout is 15 minutes, as I just said. Concurrent execution at 1000, but this can be increased. Burst quota, this can also be increased. The invocation payload for synchronous events is 6 megabytes, for asynchronous is 256 kilobytes. You can also package your lambdas as container images, and in this case, at most you can have 10 gigabytes for a container image. The deployment package and the max layers have also some limits. Now let's look at some best practices for lambdas. Here I have listed them. I'm not going to go through to read all these now, because we're going to discuss about each and every one of these. So let's start with the environment reuse. We should take advantage of the fact that the Lambda service reuses environments for our functions. So basically, if you look at this code on the screen, you see that we have to initialize a DynamoDB client here. So in this case, you should do this always outside of your Lambda handler. And why is that? That is because when your environment is created for you, the code which is here, this will be run in the initialization phase, so the cold start phase. And then the handler is invoked when you have a warm invocation. So if you did the initialization outside of the handler, when you're going to have a warm invocation, the client will be already initialized for you. So your handler code will not have to spend time initializing that. And that leads to a faster execution. Because here we are initializing DynamoDB, but you could have something that takes more time to initialize. So take advantage of that. Also, you should use the /tmp storage as a cache, because as I said, in case of a warm start, you have this preserved from the previous run. So if you look at this code snippet, so basically what we're going to do, we're going to try to read this file here, this /tmp/carconfig.json from the tmp storage. If it's not there, we're going to load it from S3, you see here. And after that, we're going to write it to the /tmp storage. And then our next invocation in the same warm environment will not have to read it from S3, it will just have to read it from the tmp storage, which is much faster. Also, here you might have something else, not S3, but some external service that takes longer to load from. And in that case, it's ideal to have a local cache of that data. Now, you should know that this /tmp is temporary, so it's only living in the same execution environment. And you know that each environment is destroyed after about 10 minutes at most. So you have to find some way to store your state in some external storage. And the most often used services are DynamoDB, for example, the Simple Storage Service or S3, Elastic Cache, and the Elastic File System. And let's look at a little bit of a different situation. You have to store a 15 gigabyte file to process it with your Lambda function. So what you're going to do, because your environment, the temp storage is limited to just 10 gigabytes, so you cannot put it there. Even if you would have a smaller file and you put it there, after a while it's, let's say it's 9 gigabytes. And after the execution environment is destroyed, you lose it and you have to load it again from somewhere. This is not ideal at all. So in that case, basically you have to find some other way. Maybe all your Lambdas, all three environments have to have access to the same file. In that case, you can use the Elastic File System or EFS. And EFS is a file system that you can attach to Lambda functions, but not only Lambda functions, also EC2 instances and other services. And basically, your Lambdas will all have access, all three environments will have access to the same EFS file system. This is just like you having a NAS device in your home. I'm not sure if you know what a NAS device is, a network attached storage. I have one at my home, so basically I put all my files there and my laptop can connect to it, my smart TV can connect to it, my smartphone can connect to it. They all have access to the same files, my pictures and so on. The EFS file system is similar. So you just have one EFS file system with a copy of your file, and all these environments have access to the same file. And let's say you might have situations where other systems have to interact with the same data, like for example an EC2 instance or an AWS Fargate cluster. These can all interact with that file. So that is another way to optimize your Lambda function. Also, you should pay attention to the deployment package size. So take advantage of layers, but don't overdo it, because layers might have also, you could run into issues if you have too many dependencies there, and some other issues that might come up. Do not include unnecessary libraries, so stick to only the libraries you need, because loading unnecessary libraries will take away time from in the cold start phase. Also, do not include the whole AWS SDK library. You just have to include the components that you need, and here we have this link at the bottom in which AWS explains how to use only the specific components that you need from the AWS SDK. And also use simpler frameworks. For example, many people I've seen that they are using complex frameworks such as Express.js, for example, and loading that in the Lambda function. And that is in most cases unnecessary, because you can achieve that in other ways, what they're trying to do. But I can understand that in some cases where you're doing lift and shift migration of Express apps, you can start with that, but then try to optimize that and reduce the deployment package size. Then you also have database connections that your Lambda function has to do. So let's say you have an RDS database, MySQL or PostgreSQL or whatever, and your Lambda has to open a connection to RDS and read something. But you have a second Lambda which has to do the same thing, and so on. Up until, let's say, you have 1000 concurrent Lambda runs. What's going to happen in this case is that you have this high concurrency, and your RDS database or other database might run out of available connections. So that is also happening because it's not possible to close the connections easily. You don't know when your environment is being terminated. I mean, you could know with certain extensions if you create an extension, but that is complicated to do. So you're not closing the connections, and the available database connections are exhausted. And this has a solution. So basically what you have to do is introduce a so-called RDS proxy between the RDS database and the Lambda functions. And this RDS proxy will open a connection or more to the database. You can define how many connections and what percentage of the database's connections should be taken. And then this will communicate with the RDS database for your Lambda functions. You should know that this is a paid service, so it's an extra cost. So you have to put it in balance if you need it or you do not need it, really. Another thing that you should pay attention to is to wait for background processes to complete, because let's say you have a Lambda which starts a process, and that process is doing something, and then the second Lambda is started, and that is reading some variable that was set by the first one, but the process ran and modified it. So you can have unexpected results if you leave background processes to run between two different invocations of the Lambda. And each language has specific methods of handling this. You can use callbacks, async await for Node.js, for example. Then provisioned concurrency can also be used. This I mentioned earlier. So you can use this to mitigate the problems that you have with cold starts, for example. So basically, if you have a provisioned concurrency of 2, then the requests that are coming in are routed to the warm environments, and those will have a faster execution because they don't have a cold start. And the third request, which does not encounter a provisioned environment, will have a cold start, and that will take longer to run. At last, reInvent AWS announced Snap Start. This is a feature that allows you to improve the startup performance of Java Lambda functions. So this is only available for Java 11 and 17 managed runtimes. So basically only specific runtimes that AWS maintains. And this works by creating a snapshot of the memory and the disk state of the function. And then your Lambda execution will be faster. Now, another thing I want to discuss is having granular functions versus lambda-lets. So what this means? This means that, for example, you have an API gateway, and in this API gateway you have certain paths. You have create user, update user, delete user, get user, and each of these will have attached a different Lambda function. So you will have a Lambda for creating users, you will have a Lambda for updating users, deleting, and so on. This is one way of doing it. This is having granular functions. And the advantage of this is that you can set a fine-grained security configuration on each Lambda. So if your Lambda only has to, let's say, read a user, you will only give it read permissions and not write permissions. Also leads to a lower size of the Lambda function overall, so it's easier to migrate, update, and easier to work in multi-team setups. However, it has also certain bad sides or cons. It can come with higher cost in certain situations. For example, if you have third-party applications that interact with your Lambdas, or for example monitoring applications that monitor the Lambdas, and you have to pay based on the number of functions you have. This is a situation that I've seen before. So in this case, having a high number of Lambdas will lead to a higher cost with that third party. Also, it has a higher management overhead because you have to have a lot of the Lambda functions, and you have to know which one, what it does, and deployment for each of these functions have to be configured and so on. So this is something to keep in mind. Then we have the lambda-lit, or the model where you have all your routes handled in the same Lambda function. So you have create user, update user, delete user, get user, all in the same Lambda function. This is called a lambda-lit. And the pros of this is that it has a lower cost in certain situations, and you have less management overhead. But it has also some cons, like you cannot define security per route or path. The Lambda overall will have a larger size, so it might lead to a cold start. It's hard to migrate, update, reuse code, also to test, and working in multi-team setups could prove challenging. Also, AWS lists this lambda-lit as an anti-pattern, but I would say that take this with a grain of salt. So it's always in architecture, it's about trade-offs. So you have to see which model is more suitable for your application. You could go for granular functions or lambda-lits. Okay, let's see a little bit about Lambda power tuning. So as I said, the Lambda memory can go from 128 megabytes to 10 gigabytes, and the CPU will increase proportionally with the cost. And the Lambda runtime can go from up to 15 minutes. So the more runtime you have, the more cost you will generate. And you have some tuning options here, because if you increase the memory of your Lambda function, you also increase the CPU, and in some cases that could lead to a faster execution. So instead of running for 5 minutes, your Lambda will only run for 2 minutes. So basically you have saved on the duration. Also, some other thing that you have to think about is that you, in some cases, you might need to lower the timeout, because this could terminate stuck functions earlier, so you will have less cost. What do I mean by this? So let's say you put the Lambda timeout at 15 minutes, the maximum, because you say, okay, if I have 15 minutes, let the Lambda run as long as it needs. But you might have a buggy Lambda, which for some reason runs for 9 minutes or 10 minutes, and it stops, it remains stuck for some reason, or errors out, and you basically pay for all that time. Now, if you know that your Lambdas usually run for 2 minutes, and add some additional time on that, and then set the timeout at 5 minutes or 7 minutes, I don't know, and you don't have to wait then up until 9-10 minutes until your Lambda errors out, so you will have less cost. There's also a tool called AWS Lambda Power Tuning from Alex Casaboni, who works at AWS. This is an open source tool which will try different configurations for your Lambda function, and then you will be able to see which is the better configuration in terms of memory and timeout for your Lambda function. There's also a tool called Power Tools for AWS Lambda. This is a developer toolkit in which you can use to implement serverless best practices. It has a bunch of components listed here in the right side. I have to tell you the truth that I didn't use this one. I know that some people are using it, and I listed it here, but yeah, you should just look at it and try it out if it's suitable for you. Okay, now we looked at some best practices. Let's also look at some anti-patterns. So what you shouldn't do. So the first thing on my list would be Lambda to Lambda calls. So using Lambda as an orchestrator. And I have to admit that I have been doing this in my early days of working with Lambda. So basically what I did, I thought, okay, I have a Lambda, I have to invoke another Lambda, I will just invoke it from the first Lambda, call the second Lambda. But that is bad for the following reason. So if you invoke your second Lambda from the first Lambda, you will have to pay for both as long as they run. And your first Lambda will run until your second Lambda completes its execution. So you see, you are paying for your second Lambda, and your first Lambda will take longer up until the second one completes. So that is a bad idea. For that, you should use AWS step functions. And I have, I think, several videos on the channel on AWS step functions. This is an orchestration service. You can create state machines with the step function service, in which you can run Lambdas in parallel, sequentially. You can also integrate with other services directly, like S3, SNS, and so on. Just look at my video on the channel on step functions, and you're going to see why it's a very good idea to use this service instead of using Lambda to Lambda calls. Another anti-pattern is having infinite loops. Of course, no one wants to have infinite loops in their Lambda, but let's think about the following scenario. Let's say you have a bucket, S3 bucket with files. Let's say you're creating some files in the bucket, and you also have a trigger set on that bucket, which is a Lambda. So whenever someone uploads a file to this bucket, your Lambda function is being triggered. And the Lambda does some things with the file. Let's say it modifies it in some way and puts it back to the bucket. So what will happen in this case? Basically, you will have an infinite loop, because again, the object that you have just uploaded to the bucket will trigger again the Lambda function. The Lambda will write again, and so on. And this will lead to a very high cost in your AWS account. So you should avoid this. And there are some ways. Jan Kui has a very good article on how to detect and stop accidental infinite recursions. Overall, his blog, I think, is one of the best resources to look at and learn about serverless. And you can find this article there as well, in which he explains how you can detect and stop these. Also, AWS published a new feature which helps you in detecting and stopping recursive loops in Lambda functions, but this is only available for certain services, not for all services. So check out these two links, and you will find there some more guidance on this. Another anti-pattern is not taking advantage of environment reuse, just as I told you in the best practices that you should take advantage. So if you do not take advantage of environment reuse, that is an anti-pattern. So I will not go into further details on that. So let's look at another anti-pattern, which is synchronous waiting in a single Lambda function. So what do we mean by this? Let's imagine we have a Lambda function that has to write to an S3 bucket and also to a DynamoDB table. So a request comes in, an event. The Lambda will write to the bucket. It will put an object. It will wait for a response, and then it will write an item to the DynamoDB table. And then it will get a response and respond to the invoker. Now, in some cases, you do not have to actually wait for the put object operation to finish, because the two things are not related. But still, many people are doing this. They are waiting for one operation to finish until they start the second one. So you can redo this in the following way. So use parallel operations instead. Event comes in. You start the put operation and the write operation in the same time, and you will get a response from both of them and send it back. So this is faster. Of course, this is not possible in all cases. In some cases, you really have to wait until for the put object to finish, because you might need some result or something like that. In that case, you can split the Lambda in two different Lambdas and have the following workflow. So put the event to the first Lambda, which puts the object in the bucket. You set up a trigger on the bucket. That trigger will invoke a second Lambda function, and that Lambda function will write the item to the DynamoDB table. So this is how you can improve this. Then you also have an anti-pattern is that many people use manual processes, for example, using the AWS console to write code. So using the console to test out things and play around, it's fine. But when you have production environments or developments, it's not a good idea to use the AWS console. Use an editor, an IDE, and have a proper deployment pipeline. That is also an anti-pattern, not having pipelines for automatic deployments and testing of your Lambda functions. This is actually possible, and I have a video or two on the channel on that. Also, ignoring monitoring is something that many people are doing from my experience. and you should always monitor your Lambda functions, monitor for cost, for errors, for all kinds of things. Then finally, ignoring idempotency requirements. So what is idempotency? So in some cases, some events are being delivered twice to your Lambda function. This is because maybe the client timed out, but it managed to send the event, but it thinks that it did not, and sends the event again. Or there are services like SQS which have at least once delivery, meaning that they can deliver the event multiple times, the SQS message in this case. And we want to make sure that the same call with the same payload repeatedly will produce the same result. In other words, making multiple identical requests has the same effect as making a single request. That is because, think about it, if you have an order coming in, you don't want to process the order twice if for some reason it's being delivered twice. And in case of SQS, for example, you can rely on the message ID, but this is not always reliable because you might really have two different messages. That can happen when the client doesn't realize that he already sent a message and sends another one. In that case, the message ID will be different, so you cannot rely on that. Instead, you could create a hash of the message payload, like the order itself, and put it somewhere. And if you encounter the same hash a little bit later, you know that you have the same order coming in again. Of course, you have to store these hashes somewhere, probably in DynamoDB or something like that. Okay, so that was about it. This was my live stream today on writing scalable Lambda functions. I hope it was useful for you and you have learned something new. If so, please subscribe to the channel, give the video a like, and I hope to see you soon here on the channel with another video soon. So have a great day.